Okay, perfect. Um, you can go ahead and lower your hand. Okay, so let's see a couple of quick things, administrative issues. The first thing is, let's see, let's go to the, let's see, current courses. Where do I log in? Okay. Okay, so a couple of links posted on YouTube. Okay, on Moodle, link to a YouTube playlist that's posted on YouTube. So what I did was to create a YouTube playlist of the recording of the classes that's available as a playlist. You have access to that if you want to view the class at a later time. Now the class annotations and notes are also posted online on Google Drive, and the link to that is posted here as well. Okay, so that's Google Drive. The other thing is I posted here on EEE 108 Moodle page the link to do the Zoom session. I know you already know how to get here, um, except that I want to make it convenient for you, so I made that availability. Okay, that's one thing. The other thing is EEE 108L is available now. Okay, let me go there. 108L is available here. Okay, so what you can do is you can go ahead and get started enrolling into this. You can begin by enrolling into this. Okay, so the first lab is Introduction to Spice. There will be no lab session this week. We will begin our labs next week. But before that, by a show of hands, how many of you do have access to the lab component already? Okay, handful of you. Okay, one of you. So that's one of the reasons why we can wait out just this week. Okay, so what we will do is next week we will do introduction to Spice. Okay, so the lab videos are posted by Dr. Perry Headley. So you can click on this video introduction and then see what this course is, what this lab is all about. And I'm not going to go through that exercise, but then what I want you to do is to work on the pre-lab for each lab. Hopefully, by the time we are finished with the first lab, which does not need any physical components, it's all online. By the time you are done with that, hopefully you're able to receive the components. Okay, so the first lab does not need any components, so we will wait. We will wait this week. Next week we are going to get started with lab 1, Introduction to Spice. Okay, Introduction to Spice.
I have a question. Like,
Yes, question.
do we need components or something for the labs?
Yes, you do need components. Let's see, if you go to Canvas. Okay, so I have been sending emails left and right since a week ago or so, a couple of weeks ago or so. So let's see how many of you, by a show of hands, how many of you received the emails that I have been sending about ordering lab components? Okay, so good. Good that a bunch of you have received. Okay, go ahead and lower your hand, please. Okay. Okay, now by a show of hands, how many of you already ordered the components online and you're just waiting? Okay, just one person ordered online. I know a bunch of you, a couple of you ordered online, others as well. Let's see something in the chat. In the chat. Okay, I know a few of you ordered online. So what we'll do if you did not already, are you talking about, mine should be arriving Friday, mine should be arriving soon. So I know many of you ordered online. So if you're waiting, what we will do is we will let this week pass, and beginning next week, we'll begin with a lab that does not need any components. I'm talking about Hydra, Muhammad Ravi, you're right. Dawoodza, Muhammad, you're right. I'm talking about working on Hydra, a university server that gives you access to simulation software. So for the first lab, you do not need any components. We will begin next week. Okay. So some of you are waiting on the parts to arrive. Okay, very good. You can go ahead and lower your hand. Okay. Now, for those of you who did not receive the announcement, or those of you who registered into the course very recently, okay, I posted a bunch of announcements on how to order parts. Okay, if you go to Canvas, if you don't know where to order parts, you can go to Canvas. Okay, you go to Canvas and look under announcements. You should find some information about ordering analog discovery 2. I provided a bunch of options, 3 or 4 options. You can see what works best for you. Okay, you can either choose to buy the analog discovery 2 as a bundle for about $230, or you can choose to buy them separately. You'll save around $25 if you buy the parts and the analog discovery board separately. Those of you who already have analog discovery 2, and those of you who just want to order the components, okay, you can go to just the components, ordering the components, so on and so forth. Okay, so the idea is there are a bunch of options, explore those options. Another important thing is you do not want to miss the student discount. There are a couple of discounts that you should not miss on Digilent. Okay, when you're buying this analog discovery 2, let me see, when you're buying the analog discovery 2, so if you go to announcements under ordering this guy, okay, ordering analog discovery 2, I posted a bunch of announcements, so you can look at what option works best for you. Okay, so there are a bunch of recommendations, and you can mix and match. But the idea is you definitely don't want to miss the academic pricing. There are 2 ways you can reduce the price. You can get the academic pricing, okay? And on top of that, at the checkout time, make sure you apply the coupon code here, okay? So 2 ways to make sure you get the lowest price. And I would say if you did not already order, you should order pretty soon. And the idea is that you share your lab components with another person. You'll be working in a group of 2 students. Okay, so sooner than later, you're going to have to figure out who your lab partner will be. And for that, you may want to use the lab discussion forum. Okay, I'm going to add a new discussion topic right away. Okay, so what you can do is post to forum. Post messages cannot be help choose partner. Pinned tags, post to forum. So you can use that forum, lab partners forum discussion to look for lab partners or collaborate. Okay, so that's fine with me. Or if you want to, if you have an extra board, and or if you need a board, you can use this. You can use this lab discussion forum. Okay, questions, please. So I'll talk a little, why don't I talk a little bit more about the lab? Okay. So the lab, the core requisite is 108. So I thought long and hard about how best to assign the grades for the lab. Okay, given that summer is an extremely short semester, just 6 weeks. Okay, I did not want to burden you with the exercise of having to write long, lengthy reports. So there are only two components to each lab. You have to do a pre-lab, okay, which is to work on the lab ahead of time before you can get started with the actual lab itself. So you can do the pre-lab, which includes piece-wise simulations and hand calculations. And then you actually physically hook the components onto the breadboard, and that's what, and do the demonstration. That's worth 50%. Okay, so there are two components to each lab. You do a pre-lab, you do simulate it first and see its action in software simulation. You do AC analysis, DC analysis, and whatever analysis is relevant. And that's worth 50%. And the physical demonstration in lab is worth another 50%. So it's important that you find a lab partner. Okay, for the pre-lab, you do have to submit a PDF. Okay, so what you will do is you will take a screenshot of the simulation results, any hand calculations, and any observations. You put them all into one PDF file and to upload that to Moodle. Okay, and when I take a look at that and grade it, I assign you 50% and let you begin on the physical lab itself. Okay, so make sure you find a lab partner pretty soon, and then make sure you order the lab component if you did not already. Okay, and if you have difficulties, financial or whatever, or you have some kind of inhibitions in acquiring a board and you don't like that, or for whatever reasons, let me know. I'll see what I can do. Okay, but either ways, it is very important that you make an arrangement to find a lab partner and understand what constitutes a lab. Okay, what goes into getting credit for the lab. Okay, 2 students per group. Okay, so the first lab is Introduction to Spice Analysis Techniques. That's lab 1 next week. Okay, so as you can see, everything is pushed back by 1 week. Okay, we may have to make some uh, adjustments somewhere along the semester to accommodate the pushback. But the idea is next week we are going to get started with Introduction to Spice Analysis Techniques. Okay, that's about the list of labs throughout the semester. And what you want to do is um, to make sure that you have um, a good idea of who you're working with. Okay, then for the first lab, as you can see, each lab has a video introduction. Okay, each lab has a video introduction. Okay, video introduction. Okay, similarly, this lab, each lab has a repository to submit piece-by simulations and hand calculations. So that's your pre-lab. Okay, that is where you will submit your PDF document. Lab 1 piece-by simulations. Lab 1 demonstration and discussion. You don't have to submit anything for that. I'm going to grade um, based on your demonstration. Okay, so make sure you have access to a camera and make sure um, you divide the work between your partner and yourself. Questions, please. Okay. Now, in a regular semester, there was lab quizzes as well, but I disable the quizzes. There are only two components for the lab. You have to do the pre-lab and you have to do the demonstration. No report or no quizzes. Okay. That said, in addition to this, there's a lot of additional resources provided for you. Okay. The first thing you would watch is the PSpice video demo. Okay, right under the tab of general lab information, right at the top of the page. Okay, there's a PSpice video demo link that takes you to Dr. Hadley's website repository of a media site collection of his videos. So you really want to make sure that you watch these videos and thoroughly understand. Okay, these simulations, this software, you don't have to download the PSpice software. It's already installed on Hydra for you. Okay, so that is where you would need to go. Okay, PSpice video demos. Questions, please. Something in the chat. I desperately need a volunteer to keep an eye on the chat window. I cannot, I simply cannot, keep up with that. Can it be a group of 3 people? It is groups of 2, ideally, under very rare circumstances. If you explain uh, the motivating reason as to why you want 3 um, lab partners, maybe I will consider. The reason is there's only 2 components here. There's the pre-lab and there's the um, actual lab demonstration itself. So trying to work out the logistics between 2 partners itself is hard enough. But if you add the third one into the mix, one person may end up doing all of the work. The other person may just be playing a little bit of a supporting role. The third person, lab partner, might be very dormant, or they might not come out learning a whole lot. So I try to discourage you from joining into groups of 3, but if you can come up with a very valid reason as to why you want to work in a group of 3, I definitely take a look. Other questions, please.
Uh, Professor, like for the Hydra, like I was not able to assess it. Do we need like do Windows 10 support it?
Windows 10 does support it. So why don't I switch the screen here to my laptop and maybe I'll try showing what to do. Okay, why
Okay,
don't I
thank
do
you.
that? I'm going to share my screen from my um, iPad. I'm going to switch to my laptop. Maybe I can try showing. So how do you access Hydra? Okay, let's see. Just give me 1 second. Let's see. Just give me a second. Okay, so here, the first thing I would do is to download what is known as Global Protect. Okay, Global Protect is a VPN that you need to log into before you can access any of the campus resources. So make a note of that. You need to download Global Protect, which is a VPN service, and it should be available. I don't know, I did not download it recently. I'll still see if I can see US Global Protect. Maybe I can VPN right here. So there is some information on where to download and how to use it. It's really easy. It's not all that difficult. Let's see, Global Protect download. Software tools, VPN. If you go to information, IRT, Information Resources Technology, in the softwares. Okay, so I'm at CS. I simply did a Google search of Global Protect, and somewhere in there in the list, you should see an option to download Global Protect. Let me find it. Global. Okay, right there. Okay, I looked up Global Protect on Google, and I did a search for that Global Protect using the word, and I can download Global Protect for my machine here, Mac, Linux, Windows 32 or Windows 64. Once I do that, what the first thing I need to do is to log into that VPN service. So global. Let's see. I'm trying to connect, and it should. Okay. Okay. So there's a two-step verification process that it'll go through. Okay. So I'm going to receive a push on my iOS and approve the push on my iOS. So now, when I click on this, and the system is incredibly slow here because I'm doing a bunch of things. I'm doing a screen recording, and I'm accessing the VPN and using Zoom. So on the bottom right corner here, you should see a globe symbol with a little check mark. Okay, so that means I'm connected to VPN. Now, if I try to, I can connect to Hydra. Okay, which is campus resources, campus servers. So I go to this guy and remote desktop. Okay. So I'm trying to, this is all in an effort to connect to the software that's installed on the ECS servers. Okay. I don't know how well you can see it, but there is a hydra.ecs.csus.edu. Okay, if you want, what you can do is you can pinch in, zoom out on your Zoom window. Okay, now in the username you would type in capital ECS slash your ECS username. Okay, so ECS username, that's how you would connect a remote desktop Hydra. That's the server you want to connect to. Okay, and once you do that, it's going to authenticate and establish a connection to Hydra. You should be able to access the software that you need from there. And since we are here, I'm going to quickly, in a minute, show you the software that we need to access. It's a slow process. It does take a little bit of time. Okay, let's see if I can bring it over. Okay, I'm going to close this out because so this is what Hydra looks like. The banner on the top tells you that you are indeed connected to Hydra. Once you see that banner, you know you're connected to the ECS server. Then in the Windows button, when you press the start button, you should see a bunch of software installed. You should see a whole bunch of software installed. But you are interested in Cadence release 17 to 2016. Okay, and in that there's a whole suite of tools, but you're only interested in Capture CIS. Okay, Capture CIS, and all of this information is available on the video lectures as well. But then if you're having difficulties, you click that, it's going to pull up some software, it's going to pull up a choice, and then all of this is explained. I'm not going to go into the actual lab itself right now because that is going too far into the procedure for the lab. But then this should at least hopefully give you, now I'm going to, why don't I end the Hydra connection here, okay? That should at least give you the process to get started, okay? In order for you to be able to access the ECS software, the first thing you have to do is to get Global Protect, okay? Configure Global Protect, it's an easy step, okay? Log into the VPN. You have to connect to Global Protect and then use Remote Desktop. Okay, so it's a two-step process. Use Global Protect and then Remote Desktop. When you're doing Remote Desktop, you have to do hydra.ecs.cscs.edu. Okay, that's the server name. hydra.ecs.csus.edu, and the username would be your ECS account. ECS / your ECS account. Okay?
Okay, thank you.
To do here is to switch back to my iPad and see and continue from that. So let's see something in the chat window. Let me first of all start by sharing the screen on my iPad. Okay. Miss the directions for pre-lab work for lab 1. What work you like to see? Okay. So the question is, what is necessary for the pre-lab 1? Okay. For pre-lab 1, lab 1 is kind of a unique lab in the sense that it's an introduction to Spice. So you will do screenshots for pre-lab work, and this is true for any pre-lab work. Any pre-lab, you have to do your simulations in PSpice. So set up the project on PSpice, access the software using remote desktop Hydra server, set up your simulations, do your schematic. What I'm looking for is a PDF of the screenshot of all the, when you follow the lab manual step by step. Okay, when you, I'm going to open the lab document here really quickly. Okay, so it tells you what to do step by step, the Spice simulations that you want to set up. Okay, what you will do is you will create a screenshot of your schematic and of your simulations. There are a bunch of simulations. You do a DC sweep analysis, so on and so forth. Okay, so as you follow each of these steps, part 1, part 2, part 3, you will do DC analysis. You'll do screenshots of all your lab. And in addition to that, you will also do the hand calculations necessary. Okay, so you'll do the hand calculations. So any lab that you do, when it comes to the pre-lab, what you will have to do is to do the screenshot of your simulations and hand calculations. Put them all into one PDF file and submit into the lab 1 PSpice sims and hand calculations. Okay, so when you look at the title, lab 1 PSpice sims and hand calculations, that should tell you what is included in the pre-lab. Okay, Jose, did that answer your question?
Yes, thank you.
Okay, yes, other questions, please. All right, when it comes to working in groups of 3 students, I really have to be really convinced to see a reason for that. Okay, if there are other reasons, like you'd like to share the cost between 3 of you rather than 2 of you, that may be coming at a cost. You're only saving $20 or $30 or maybe $40 when you share across 3 students. But but that saving may not be worth the learning that you forego. What about working as one? Sure, you can work on the lab um, by yourself, but if you are open, I would encourage you to partner with somebody. So you're helping somebody who does not, you're helping somebody share the costs with you, and you're also sharing the burden. So I don't stop you from working on the lab by yourself, but I strongly encourage that you work in groups. Okay. Other questions, please. Okay. So that's about the lab. So the first thing you want to do is to enroll into the 108L using the access code EEE108. Once you do that, you can go ahead and watch all these videos, PSpice video demos. Okay. Once you watch all the video demos, you can get started with lab 1. Okay. You can get started with lab 1. And I just showed you how to get started with lab 1. Download Global Protect, access remote desktop, and then access the software. Okay. And then as you follow the video step by step, it will give you really nice breakdown of what you need to do. Okay. Questions? Well, what you can, the question is, how can you register as 2 partners? The first thing is you want to find a partner, and once you do that, and when you work in tandem with your lab partner, when it comes time to let me know, that'll be the first lab. In the first lab, um, when I break you out into breakout rooms, into separate groups, that is when I put you in different groups. So when it is time for the first lab next week, I expect that you have your lab partner and that you're already beginning. You already began the work with your lab partner. Okay, that is when I will register and I will go ahead and group you together as a group next week. Okay. Other questions, please. So for now, all you have to do is find a partner and begin working with them. Next week, when I begin the lab, that is when I will enter that into Moodle. Okay. Other questions, please. All right. So let's continue from where we left off in the last class. Okay. So that's about 108L. Okay. So this is what we did in the last class. Introduction to signals and amplifier basics. Okay. Okay. I mentioned that anything, any information that is sent via voltage or current, that can be considered as a signal. Okay. Anything that has any piece of information, that's called a signal. Okay. The real world is all analog, and then the digital domain, microprocessors, microcontrollers are all in the digital domain. Okay, and we have to have a way of converting from analog real world to digital domain, and then back to analog real world signals. Okay, on the left is an analog signal, which is continuous in time, continuous in value, infinitely possible real values. On the right hand side is a digital signal, which can only take quantized or discrete values, discrete in time, discrete in values. Okay, so we have to have a way of rounding up. So when you convert from analog to digital, there is always going to be some kind of signal lost owing to the fact that there is a rounding error. Okay, that's the idea of quantization, rounding up and rounding down. That's what we looked at in the last class. Okay, so we looked at what constitutes an analog signal, analog to digital conversion. Most of the signal processing is done in the digital domain, and then there is the digital to analog converter to convert your signals back into the real world. Okay. Obaid has a question. The demo will be next week, correct? So Monday of next week, when we meet for the EEE 108L class, that is when, before the end of the class on Monday, you will be doing a demo. Okay, if it is just software, you'll just do the software demo. Okay, each lab, each class, Monday and Wednesday, each of those, each of the times we meet in the lab, there's going to be something new. The demo will be by the end of the lab time. Okay, and then we looked at the idea of voltage and current signal models, voltage and current signal models in the analog domain. Okay, and I mentioned there is Thevenin's equivalent for a voltage source, and there is a Norton's equivalent for a current source. Okay, there is the source resistance RS. RS is always used in series with the voltage source. It's used in parallel with the current source. Okay, and because there is the source resistance RS, there is going to be some voltage current lost. Some of the signal is lost because of the resistance RS. Okay, the source resistance RS. Okay, if it is a voltage source, I want the RS source resistance to be very, very small. Okay, so that the amount of signal lost is small. If it's a current source, for a current source, I want the source resistance to be really, really large, so that the signal lost is, the current signal lost is small. Does that make sense? So this is what we discussed in the last class. Okay. And then we talked about the idea of frequency spectrum of signals. Okay, if you look at the distribution of voltage, power for a given signal at different frequencies. So if the x-axis is frequencies and the y-axis is volts, as in the figure bottom, right? This guy. Along the x-axis is the voltage, along the y-axis is frequency. Then you have a frequency spectrum. Okay, so here is the idea. We talked about the notion of Fourier series. Okay, what's the idea of Fourier series? Who can remind me what the idea was?
Is it that any periodic signal can be described as a sum of sinusoidal signals?
Thank you. You said it much better than I said it in the last class. Any repeating periodic signal can be expressed as a sum of sinusoidal signals. Okay, so to denote that fact, each line here represents one sinusoid. So the idea is that if you represent the square wave in a frequency domain, okay, that can be expressed as a really big sinusoid at omega naught frequency, and a small sinusoid at 3 omega frequency, and a much smaller sinusoid at 5 omega naught frequency, and a yet smaller sine at 7 omega naught frequency. So you can add up a bunch of sine waves to create a repeating square wave. Okay, and that is shown in the frequency spectrum here. Okay, the higher frequencies are called frequency harmonics. Okay, and I mentioned there are a bunch of different ways to process the signals. There can be amplifiers, there can be filters, there can be data converters, analog to digital and digital to analog, and there can even be phase lock loops, comparators, AC to DC converter, a whole host of different ways in which I can manipulate, massage, and um, and modify my input signal. Okay, questions, please. Questions so far. Okay, and I then went into the idea of an electronic system example. Okay, on one side, so let me eliminate this. Okay, okay. Okay, so from the real world, sensors gather information. Okay, they do some kind of processing in the analog domain and then convert the signals into digital domain. Okay, once in the digital domain, most of the signal processing is done by the microprocessor. Okay, and then once the signal processing is done, it is converted back to analog domain, and the analog domain sends it to actuators, which modify the value of the signal in the real world. Okay, so incoming can be sound, a microphone. Okay, that could be a sensor, and then after doing a digital signal processing, you can output to a speaker, loudspeaker. Okay, by amplifying the signal. There's a loudspeaker right there. Okay, here is the microphone coming in. So this is the typical electronic system in which you sense some kind of real world signal, modify the signal, maybe amplify it, maybe cancel the noise, do whatever you have to do, and then pass it as an output. Okay, analog and digital electronics, there can be a whole list, a whole range of signal modifications that we can do. Okay, amplification, filtering, comparison, using it as buffers, current voltage converters, analog digital converters, wave shaping, so on and so forth. And the list is really, really long. Okay, so that's the typical flow of a signal from the real world all the way into the digital signal processor and into the real world back again. So that is how far we went in the last class. Okay, so let's look at this guy. So let's move further by talking about amplifiers. So amplifiers are the most basic signal processing operation there is. Okay, so for example, let's say I have an input signal. Let's say it is too small and I want to magnify that. Okay, what I can do is I can pass this through an inverter, through an amplifier, so that the output, so this guy is, you pass it through an amplifier. The input is a small signal. The output is an amplified, a magnified version of the input. Okay, so that's the simplest, most basic signal operation that we can do. Okay, amplifiers provide what is known as gain to make signals bigger. So this guy, a fundamental characteristic of the amplifier is gain. Okay, gain. Signals are typically measured between two terminals. Okay, notice there are two versions of amplifiers shown here. The one on the left is called a differential amplifier. Okay, where the inputs are measured as the voltage difference between two input terminals, and the outputs are also measured as the difference between two output terminals. They're differential, okay? They sense the difference between two terminals on the input, and they show the output as, the output is also measured as a difference between two output terminals. Look at what's going on there, right? It's called single-ended. Single-ended amplifier in the sense that one of the terminals, if you make one of the terminals a ground, then you have a single-ended amplifier, okay? Where the input is measured as the difference between that guy and ground. The output is also one terminal and the other terminal is ground, okay? So that's the idea. When one of the terminals is ground, it's called a single-ended amplifier. So I can have a mix of these. I can have an amplifier that looks something like this, okay, which is single-ended output, that but differential input. Okay, so this is a differential input, and the output is single-ended. Because the other terminal on the output is ground. Okay, so there is V1 over here and V2 over here. The input is differential, the output is single-ended. Okay, one of the output terminals is ground, so it is called a single-ended output. Okay, so differential amplifiers measure signals as the difference between two different terminals. Okay, when one of the terminals is ground, it's called a single-ended amplifier. Okay, there are different types of amplifier gain. Okay, depending on the input. So I'm going to give you an expression here. Output is gain times input. Okay, our gain is defined as output over input. Okay, and in this case, the gain happens to be voltage gain because the output is a voltage and the input is a voltage. So I have a voltage gain. On the other hand, this guy is a current gain because the input is the output is a current and the input is a current. Okay, there's a current gain. So if you look at the top here, for the same amplifier, if I look at V output over time over V input over time, so that's this guy over that guy, output over input, then I have what is known as voltage gain. That's the definition of voltage gain. I can also define the current gain, AI, by looking at the output current, which is this guy. So output current, I0, over the input current, that guy, I1, I. Okay, so the gain can be defined as output over input. If both the output and input are voltage signals, then I have a voltage gain. If both of them are current signals, then I have a current gain. I can also have a power gain, okay? Power signals, where it's the power delivered to the load over the input power, okay? That's called the power gain. Okay, I'm showing you just two types of amplifiers. There's a voltage amplifier, there's a current amplifier. Okay, there can be more kinds of amplifiers, and I'll talk about that shortly. Okay, but depending on what type of output and what type of input I have, I can have different kinds of amplifiers. Okay? So it's always gain is usually has a pretty big range. The gain has a pretty big range when you're dealing with tens of thousands or hundreds of thousands. It's convenient to express it in terms of decibels, okay, in terms of dB, okay. When you want to express the gain in dB, all you have to do is, let's say you want to express the voltage gain AB in dB, all you have to do is take the magnitude of that, okay, and evaluate the log base 10 of that and multiply that by 20. Then you have the gain in dB. Okay, the same for current gain as well. Take the magnitude of the current gain and then apply a log base 10 of that, multiply that by 20. Then you have a current gain in decibels. Okay, now power gain is slightly different. Power gain is 10 times log base 10 of mod power gain. Okay, that's the idea. So when you're expressing in decibels, it simply is a convenient way to log it on a logarithmic scale to express, to see the range, to see a very large range of numbers. Okay, so a few intuitions for us. A 20 dB increase simply means there's a 10-time increase. Okay, a 10-time increase. Okay, let's say the gain goes from 20 dB to 40 dB. Okay, it simply means that the magnitude of gain has increased 10x. Okay, the magnitude of gain has increased 10x. Okay, if there's a 60 dB, then it simply means there's a further increase of gain in 10x. Okay, so the idea is for each 20 dB increase in gain, the magnitude increases tenfold. Okay, that's 20 dB. 6 dB increase means there's a doubling of the magnitude of gain. Okay, so if it is negative 20 dB, that implies a decrease. If it's a positive 20 dB, that implies an increase. Okay, an addition of 20 dB of gain means the gain has increased tenfold. A reduction of gain by 6 dB means the gain has halved. Okay, so that's a few notions that are convenient for us if we remember. Okay, what is not shown earlier is the idea of power supplies. If you look at the amplifier here, it almost appears that it takes a signal here and simply magnifies it. Okay, but without any help. Well, there is no such thing as a free lunch. This kind of amplification comes from power supplies. What are not shown are the power supplies. An amplifier does need power supplies in order to operate. Okay, so the power supplies that are shown explicitly here, pay attention to VCC, that's the positive power supply, and VEE, that's the negative power supply. Okay, the negative power supply is connected to one of the negative terminals. Okay, the negative terminal here, and the positive power supply is connected to the positive terminal over here. Okay, most oftentimes what we do is we simply don't show this explicitly, the big bold VCC battery line. We simply imply it by pointing an arrow to VCC. Okay, and the same here as well. We simply imply the negative power supply by writing the negative arrow shown here. Okay, that's the negative power supply. So amplifiers do need power supplies to operate. Okay, some amplifiers use, let's say, plus 5 volts, okay, and negative 5 volts. Okay, what's the total range here? The total range is 5 plus 5 to negative 5. So the total power supply range is 10 volts. Okay, interestingly, the big picture operation of an amplifier does not change when we keep the range exactly the same. So in other words, if I operate the same amplifier with a 10 volt and 0 volt power supplies, within certain limits, it's still going to behave exactly similar to an amplifier operating with these plus 5 and negative 5 power supplies. Okay, so this guy, the amplifier operating with that power supplies, for all intents and purposes, is very similar to an amplifier operating with the same range, okay, but different values. All signals must stay between positive and negative power supplies, okay? So the positive power supply kind of defines the ceiling, the top voltage that is possible out of this circuit, and the bottom or the floor is set by the lower power supply. Okay, the output signal cannot go beyond the positive and negative power supplies. Okay, so in other words, let's say I have an amplifier that has a gain of 10. Okay, let's say I have an amplifier that has a gain of 10, and I'm supplying an input voltage, a sine wave, that has a 0.2 volts to negative 0.2 volts. Okay, what do you think happens to the output? The output is an amplifier, right? The output is an amplified signal. So it looks amplified like so. So what would be the peak value here? The gain of the amplifier, remember, is 10. So everything is going to be amplified by 10. So the maximum V positive peak is going to be 2 volts. The negative peak is going to be negative 2 volts. Does that make sense?
Yes.
How about this guy? How about if I apply an input voltage that is 0.5 volts on the positive peak and negative 0.5 volts on the negative peak? What do you think is going to be the value on the output? The output is also going to magnify, right? Yeah.
So 5 and minus negative 5.
That's 5 volts and negative 5 volts. Sure. So that's let me try to group them somehow, color code them. I don't know. I'm going to color code them using.
Okay, using that logic, if you were to use the example of 10 volts and 0 volts, will that sine wave will just chip about the axis? It will be all positive?
I'll come back to that question in just 1 second. Okay, I'll come back to that in just 1 second. So what happens is maybe when I explain the next problem, the next part that will become apparent. Okay, let's see this guy. Let's duplicate this and let's color code this using, I don't know, this guy. And the values I'm going to use here are 0.7 volts and negative 0.7 volts. What do you think is going to be the output?
7, 7, negative 7.
You'd expect the output to be 7 and negative 7, right?
Mm-hmm.
But for some reason, the output will not be 7 and negative 7. Can you think of why that would be the case?
Saturation point?
It's a saturation point. Remember, the VCC supplies the roof. If you're trying to jump on a trampoline, you can only jump as high as the ceiling. And the bottom is set by VEE. So what really happens is, in this scenario, in the scenario of a blue wave, where the input is this guy, and you're sending it to an amplifier of 10 volts, of 10, a magnitude of 10 gain, the output should theoretically go to 7 volts and negative 7 volts, right? But remember, don't forget the VCC, which is set at 5 volts, okay? VCC is set at 5 volts. And VCE is set at negative 5 volts. So this is positive 5, this is negative 5. So what happens is your output is going to look something like this, okay? It's going to follow all the way to positive 5, gets clipped at 5 volts because that is the ceiling set by the positive power supply. And then on the downward path, it follows the sine wave faithfully. And when it hits the bottom ceiling, it caps there, gets clipped off there, and then goes back to that. So what really happens is the VCC and VEE set the maximum saturation voltages that can be achieved on the output signal. Does that make sense? So power supplies set the ceiling. Questions, please.
So what happened to the flat area, the part that you kind of chop off out of that sine wave?
Yes, in the flat area, right here, that's how your output is going to look. Okay, when the input is like so, when the input is really, really small, remember 0.7 to negative 0.7, the output is going to be flat, 5 volts. Okay.
Will that distort the signal or what you're trying to amplify?
Yes, what happens is this node right here will show a value of 5. Okay, so in other words, I'll tell you what. When the input is increasing, okay, remember, corresponding to that, the output will increase and it will remain constant at 5, and then it will remain constant at 5. It will remain constant. It will show up as plus 5 volts throughout that range. Okay? So it will not be stored. It will just be, if you keep a capacitor, if you put a capacitor on the output, that will be stored. But what happens is that 5 is going to show up as the output voltage value. Okay?
All right, thanks.
Yes, so let's go back to the question that was asked earlier. Let's see if I can duplicate this. I want to do this, copy this. Let me see if I can paste image over here. I don't want to paste it as an image. Let's see, I can paste it, delete. Paste image, okay. No, I want to, let's see. It's the best way to paste this guy just so I can insert image. Okay, sorry about that. Let me see if I can, I'm trying to keep it as clean as possible. Okay, copy that, paste image. Okay, so ignore all of that. So what if this guy was not 10 volts? Oops, sorry. So there's only one way to do it. I'm going to clean it all up. Okay. Clean it all up and then copy. Okay. Okay. Now I can put it back on. Okay. So here, let's see if this helps. Perfect. As good as it can be. Now let's see, this voltage is 10 volts and this guy is 0 volts. Right? Ignore everything else. So the question is, whoever asked the question earlier, what's the input range that you want? Pick an input range. Do you still want to do negative 0. Plus 0.2 to negative 0.2? Plus 9 to negative 9 on the input? Plus, let's do plus 0.9 to negative 0.9 on the input. Okay, then what happens is, remember, the floor is set here to be 0 volts. Okay, the ceiling is set to be 10 volts. Okay, this is 0 volts. Okay, take this guy. I want to magnify that 10 times. Okay, so what I'm going to do is duplicate this. No, not duplicate. I'm going to style this to a different color. So this is the output. Let's pretend that this is magnified 10 times over. Okay, when it is magnified 10 times, that is how it looks, right? When it is magnified 10 times, that is how it looks. But there is something interesting that's happening here that's going to happen. It's going to clip off somewhere, and I'll show you where exactly. Okay. Okay, this is the output. Okay, the output, the ceiling is set, if you remember, by 10 volts and 0 volts. Okay, so what you will see is this is going to be magnified up to 9 volts because I have a positive 0.9 on the input. That's going to be multiplied 10 times by the gain because that's the gain of the amplifier. 10 is the gain. So 0.9 is going to become 9 times. Okay, so let's there's still 10. It did not hit the power supply peak. The problem happens on the other side. The other side, there is a ceiling set by 0 volts. So what really happens if the sine wave, the output is going to only be amplified on the positive side, and on the negative side, it's only going to be 0 volts. And then on the positive side, it's only going to go up to 0 to 9 volts. So you get a clipped wave, a wave, only the positive peaks of that are amplified. The lower half of the wave is cut off and it appears to be when the input is below 0. Does that make sense?
Yes, thank you.
Okay. So that's the idea of how the power supplies impose a positive, a higher, and lower ceiling, a roof, and a bottom on the floor. Okay, so that's the idea of amplifier power supplies. And this is where this region is called the saturation point. This is where the amplifier saturates the lower part of the wave, sine input waveform. Okay, and this is what exactly happens, clipping due to power supplies. That's the idea that we discussed so far. Okay, so instead of showing it on two different two separate sides, one on the left and one on the right, we are showing the exact same thing on the X and Y axis here. So here is the idea. Let's say this is 0.2 volts, and this is negative 0.2 volts. This sine wave is going to be amplified, assuming that the amplification is 10. So you can see that. Corresponding to that, okay? So let me be a bit more. Okay, if the amplifier gain is 10, this is going to be positive 2 volts, and this is going to be negative 2 volts. Okay, let's assume the other one, let's see, I don't know, this guy. This sine wave, okay, has the range of, what number did we see earlier that gave us a problem? 0.7, right? This gave us a problem with the clipping. That's the one I want to show down below. Okay, let's say this is 0.7 volts peak, and this is negative 0.7 peak. Corresponding to that, if you were to reflect that onto the output, okay, if you were to reflect that onto the, if you were to reflect that onto the output, you'd expect the sine wave to swing all the way top and bottom, right? But because of the power supplies imposing a ceiling, what happens is your sine wave is only, your output is only going to go from 0 to 7 volts then, or 0 to 5 volts, and then 0 to negative 5 volts. Okay, so this is positive 5 volts, and this is negative 5 volts. Okay, this part of the sine wave that is between negative 5 to negative 7, that's clipped off. Okay, the amplifier seems to be saturated at that point. So here is a convenient way shown along the y-axis here, or shown along this guy is the input. That is the input. Okay, and then the slope of this line, the slope of that line represents the gain. Okay, if the line is more slanting downwards, the gain is going to be smaller. Okay, the slope of that guy is going to be the gain, and then shown along the y-axis is the output. Okay, so the output voltage is shown along the y-axis, the input voltage is shown along the x-axis, and we can see how the output is clipping at the power supplies. Okay, so an amplifier VO versus VI, DC transfer curve. So this is the idea of DC transfer curve. So let me make this a bit clean. Clean this up a little bit. So this idea, okay, the idea of expressing the input on the x-axis, input voltage on the x-axis, and the output voltage on the y-axis, and trying to understand the relationship between input and output is called the transfer curve. Okay, all I'm doing here is, if the input is going like so, I'm trying to plot the corresponding output. Okay, similarly, if the input is going like so, the output is going to go like so. So trying to understand the relationship between input and output by plotting the input on the x-axis and output on the y-axis. That's the idea of DC transfer characteristics. Okay, and then these hard lines, okay, these lines here, these are the power supplies. That is where the maximum output or the minimum output can be. Okay, and the slope of this line, that's the gain of the amplifier. Does that make sense? Okay, good. If the output signal gets too large, if the output signal is amplified beyond the power supplies, it begins to saturate. That's the clipping because of power supplies. Okay, so that's an amplifier. And let's look at more characteristics of an amplifier that involve the input resistance and the output resistance. Okay, let's look at the input and output resistances. So the basic amplifier without any non-idealities, okay, it simply takes the input and multiplies that as the output. Okay, an amplifier V out over V in. That's the gain of the amplifier. Okay, real amplifiers have input resistance and output resistance. Okay, so and then we also know, I mentioned earlier, that the source voltage that we apply is also not an ideal source, but it has some resistance associated with it. Okay, and then here is the load that we connect. Okay, amplifiers have input resistance Ri, okay, and output resistance R0, okay, which can cause signal to be lost at both the input and output sides. Earlier, I mentioned that some of the signal can be lost because of RS. Okay, the same could happen because of when we connect them to amplifiers. Okay, so let's see which causes the input signals. Let's say I apply a voltage Vs. Let's say I apply a voltage Vs. Okay, the voltage that I am applying is Vs, right? But what do you think is the voltage that the resistance Ri is seeing?
The
Remember?
voltage divider, right? So it'd just be
Correct. It's the voltage divider.
it'd be
Correct.
the source times the input resistor over the sum of the input and source resistors.
Yes, correct. That's exactly shown here. The input seen by the resistance Ri is the voltage division, Ri over Ri plus Rs. Okay. The point I'm trying to drive home is, let's try to understand, let's try to break this uh, clumsy circuit and understand it in terms of the amplifier. Where do I see the amplifier? Okay. So the input voltage is Vi. That seems to be multiplied by some gain, okay, AV naught times VI. Okay, so that is the fundamental gain or amplifier operation. Remember? If you don't, let's go back a little bit and see. Somewhere in here, I must have mentioned that fundamental idea of an amplifier is that output is multiplied by a gain to give the input. Okay, let's see, let's paste it here. So the output, which is this voltage here, okay, see what that is. That is some gain times the input. Exactly the gain times the input is the output. So this guy is the output of the amplifier. But not all of that shows up here in the load resistance. Only some of it shows up because some of the signal is lost to RO. Okay, that's what we are interested in calculating. Okay, what we are interested in calculating is the gain between Vs and V naught. Okay, or how can we calculate the relationship between the input that is applied and the output gain that we see. So in order to get the value for Vi, which is a voltage divider, the voltage dropped across this guy is the voltage divider, Ri over the sum of those two resistances, okay, times Vs. So that gives me the voltage dropped here. That's the voltage, the input voltage here. The input voltage gets multiplied to AV naught times Vi. And then what is the output voltage in terms of this guy? So that's another voltage divider where the source is AV naught Vi times the voltage divider between R0 and RL. Okay, so that's the idea. So eventually what I have is V out is as a function of Vi. Okay, V out as a function of Vi. So the idea is, let's take a look here. Okay, let's take a look at this equation. What this equation tells me is, if I apply a Vs, okay, the input voltage, that's only going to be a fraction of the value that's applied there. Okay, so in other words, if I want all of Vs to appear on Vin, or in other words, if I want the input voltage to be as close to the V source as possible, then I want to make sure that this is as close to 1 as possible. Okay, and I can do that by making Ri extremely large. So the input resistance of a voltage amplifier should be extremely large. So if you assume this Ri to be 100 mega ohms, and this guy to be 100 mega ohms, and Rs to be a small number in comparison, then this is approximately going to be equal to 1. And then we have Vin closely following Vs. Okay, so the idea is, in order to reduce the signal loss in a voltage amplifier, the input resistance of the amplifier should be much larger in comparison to the source amplifier. Okay, source amplifier should be much smaller compared to the input amplifier. Let's take a look here. Okay, the idea is now let's try to understand what's going on here. We are interested in maximizing the voltage here, so that's this guy. That seems to be a fraction of this guy, okay, which is shown here. Okay, let's see if I can use a different color. That guy. Okay, that is determined by this ratio. If I want a big chunk of this guy to show up on the output, I want this guy to be as close to 1 as possible. So in order to make that, I want RL to be much greater than R0. That way the denominator is close to numerator. And then I end up with a value close to 1. Okay, so the idea is the R0 of a voltage amplifier should be as small as possible in comparison to the load resistance. Does that make sense?
So like the concept is like to make the value of resistance large because there will be more voltage drop, or there is it like that?
Yes, yes. I'll explain it in a different viewpoint. Okay, here. Okay, let's see. Let's just look at the input side. Okay, this is your input resistance. This is where your input is. The amplifying input is coming in. Okay, this is what you apply, and this is the resistance that is accompanying the signal source. Okay, ideally it would be 0. Does that make sense?
Yes.
You with me so far? Now the idea is you want a lot of this. There are two resistances. There is a resistance here, and there is another resistance here. Correct?
Yes.
Now what you want is, you want a lot of this voltage drop to show up across this guy, and only very small amount actually drop on this resistance. Okay, you want this resistance to be as small as possible, because there is really, you want really small drop here. You want a really big voltage showing up across this terminal. So you make Ri really, really large. You make Ri much bigger than Rs. So a lot of this Vs is going to drop across Vi. Okay, the bigger one in the series drops a lot of voltage. Okay, so let me explain the exact same thing on the other side. Okay, the idea was here. You want this voltage to show up here. So you make Ri big. Exactly similarly, you want a lot of this voltage to show up there. Therefore, you make RL much greater than R0. Then a small amount of that voltage is going to drop here. A big chunk of that voltage is going to drop here. Okay, so there are two resistances, R0 and RL. If you make RL really, really large, then a lot of this voltage is going to show up over there. Only small amount is going to drop there. Does that make sense?
Yes.
Okay. So that's the idea. In your mind, in the back of your mind, what you're thinking is, where is it that I want the maximum voltage showing up? Okay. This is just a parasitic resistance. This is a resistance that's ideally I want it to be 0. I don't want any signal lost in that. Okay. Any voltage that I apply here, well, that gets multiplied. Any voltage that is dropped here, well, that doesn't translate into a gain, right? Because it's simply dissipated. Only what you see here is multiplied there. And therefore, you want the most amount of voltage showing up here. So this voltage, you want a lot of that showing up here. Therefore, you make Ri large. Okay. Similarly, by the same argument, R0 is a non-ideal. I really like it to be 0. I really don't want any signal lost here. I ideally want all of this amplified output to show up on my load. Therefore, I make the load really, really big value compared to R0. Okay? So the one that you decide is the one that you want to dominate. Does that make sense?
Yes.
So the idea is for a voltage amplifier, you want Ri input resistance to be really large compared to the source resistance. Okay, for a voltage amplifier, you want the RL to be really big compared to the output resistance. Okay, uh, if if RS gets bigger, if R naught gets bigger, then there's going to be some signal lost. Okay, so here is an example of a signal lost. Okay, there are a bunch of different stages. There is stage 1, there is stage 2, there is stage 3. Okay, and this is the output load, RL. That's the eventual load resistance, RL. And this is the source voltage that is applied, plus to negative. So this amplifier has 3 stages. Okay, so the idea is I'm going to highlight the culprits here. Okay, the voltage that you apply here should ideally all show up there. But there is a culprit. This guy is a culprit, the input resistance. Similarly, the voltage that is amplified here should show up across this in output. But there is a culprit R naught, R out associated with that gain stage. Similarly, this happens to be the culprit that keeps all the voltage from going to the input stage there. Okay, and then there's also so all of these resistances, they happen to be the culprits that keep the signal from passing to the next stage. So in an amplifier with multiple stages, signals must be considered at the interface between each stage. Okay, so let's take the source, the large source resistance, Ri for first stage must be kept high. Okay, remember the Ri for this guy should be really, really large. Okay, the Ri should be much large compared to the Rs. Okay, so this guy, the Rs, therefore you see the Ri in this case is much large, is 1 mega ohm. That's Ri for the first stage. What is the R source? 100 kilo ohms. Okay, therefore you see that Ri is reasonably larger than Rs. So this value is Rs. This value is Ri. Okay, and therefore the first stage must be kept high. The Ri for that stage should be kept high. Okay, the small load resistance R0 for the third stage. So that explains. So that explains the fact that Ri, this guy is 1 mega ohm. Why do you think that's 1 mega ohm? Well, the reason is I want this to be really large in comparison to this guy. Okay, let's see what's going on the output side. On the output side, the load resistance seems to be 10 times the output resistance. Is that what I want? Let's see. I want the load resistance RL to be much greater than the source resistance R0, or the output resistance R0. Sure enough, because the output resistance is 10 ohms here, I pick a value 10 times that to give me the RL value. So I have, this is kind of telling me the resistances. So approximately 1% of the signal is lost between stage 1 and stage 2. Okay, between stage 1 and stage 2, if you see here, let me highlight this using the ratio of this resistance to this resistance. So this happens to be the R source for stage 2, and this happens to be the Ri for stage 2, right? If you were to ignore all of this, if you were to do that, if you were to just look at this stage, okay, as the input, the resistance here, 1 kilo ohm resistance, that's the source resistance, and this guy happens to be the Ri. This is the source resistance, and this is the Ri. So what we will do is we'll come back and talk about this a little bit more in the next class. But the only thing that we want to understand here is the ratio of each of these resistances determines the loss, signal loss between different coupling stages. Okay, so we saw the reason as to why this is really large in comparison to this, and we saw why this is 100 ohms, 10 times larger in comparison to that. Okay, we'll come back and talk about this more tomorrow. Questions, please. Questions so far? All right. I do want to remind you that videos for all of these, if you want to hear this from a different perspective, if you want Dr. Perry Healy explaining this, from his perspective, the videos are all available on the EEE 108 course as well. So that gives you a different take on how to understand these subjects. Okay, so you can use that in conjunction with the class explanation, and you can go through do the reading yourself and use that as a help to understand whatever it is that you want to master. Now, questions, please.
So you were talking about the quiz. So yesterday that we can start doing that, like first one.
Yeah.
The
You can begin starting your quiz.
Like the circuit
Let's
based.
see. So it seems there are already 28 attempts on the quiz one. So you can work on that, or you can work on the second quiz as well. Did you have the first lab is Monday, correct? Did you have another question follow-up about quiz?
Yeah, like if we have any doubt regarding any question we ask.
Yeah, you can do that. You can email me or during the lab time or before the lab time. Or if we do have time during the class time, I'll be glad to answer the questions during the class time itself. Okay. Will the pre-labs always be due on Mondays? No, pre-labs will be, remember each lab, each day of the lab, Monday we are doing one lab and Wednesday we are doing one lab. So each time you attend a lab, one pre-lab is going to be due. Okay, and that's one of the reasons. I know it's going to get extremely hectic, and that's the reason why I dropped the code. And the quizzes doesn't make sense to I have to choose where to eliminate a lot of effort from your part. So that's going to be through so each of the labs. Monday we may do one lab, and Wednesday if you do a second lab, then you have to do the pre-lab for that for Wednesday.